Good day, everybody. In Chapter 14, we discussed in great detail about the chemical equilibrium. For example, we talked about how to calculate how much product can be produced from a reaction that has reached a chemical equilibrium. We also discussed qualitatively how to predict to which direction the reaction will shift once the current equilibrium is perturbed. Today, we will discuss another aspect of this chemical equilibrium. Specifically, it's the equilibrium for acids and bases. In Chapter 4, we defined acids and bases in terms of their ability to donate or accept protons or hydrogen ions. In this section, we'll expand our discussion of acids and bases with the emphasis on the equilibrium involving the weak versus strong acids and the bases. Remember, when we initially learned this concept of acids, it was based on the ability to donate or accept protons, and this concept is so-called Brønsted-Lowry definition. For many biological systems, including humans, acid-base balance is vital to normal function and good health. Blood is regulated by the amount of carbonate and bicarbonate dissolved in it. Here, we show the balanced equation of this system. When carbon dioxide dissolves in water, it forms carbonic acid. Carbonic acid can ionize in water to give you hydrogen carbonate. And this too forms a buffer, which together with other buffer systems keeps the blood pH in a normal range. The carbonic acid, as you see over here, is one type of weak acid, and some acids are strong acids. So let's look at what are strong acids. Strong acids completely ionize in water. The keyword is 100% ionization. When we follow the definition of Brønsted-Lowry, we do know all acids and bases in water, they must react with water. And water will accept the proton from the acid. So this is the acceptor, proton acceptor. And the acid will act as the proton donor according to Brønsted-Lowry definition. If you don't remember, okay, let me remind you. That's Brønsted-Lowry definition, which we briefly discussed in Chapter 4. All right. This definition for an acid, it does not ionize directly, rather it will react with water. In which process, look at HA represents a generic acid, okay, for any acid. When it reacts with water, it donates that proton, so it becomes A minus. HA becomes A minus. At the same time, because water picks up one proton, it becomes hydronium ion. You see that? So for any acid, it's always the same. It always reacts with water and it loses one proton. It becomes the one proton less. Here it becomes A minus, and water will become hydronium ion. Okay, all right. For a strong acid, to begin with, you look at it to the left side, okay? To begin with, you have a certain amount. But after the reaction, there is no more nitric acid molecules. They have 100% ionized. Okay. In contrast, for weak acids, in the beginning, you have a certain amount. Let's say you started with the same 0.1 molar. Okay. Then afterwards, only a small amount of ions are generated. Actually, for most acids and weak acids and bases, very often you see less than 5% ionization. Here's the 6 strong acids that you have to remember. We have 3 binary acids and 3 oxyacids. You simply have to memorize them: HBr, HCl, HI, and nitric acid. Then you have perchloric acid and sulfuric acid. When you look at the definition of the acid reaction in water, they follow exactly the same pattern I just reviewed. They always, remember, in Brønsted-Lowry definition, all acids and bases, they will always react with water. Okay, you cannot just do direct ionization. That is not the Brønsted-Lowry definition. That is Arrhenius definition. All right. When they react with water according to Brønsted-Lowry, HBr will lose that H+. Similarly, HCl loses H+, loses H+. Okay, and water will pick up that H+ or proton, and they always become hydronium. All right. Also, pay attention to the arrow you use here. This arrow is one-sided to the right side because it goes to the right side 100%. That's why you use the this type of arrow. And you also look at this little bit special case for the sulfuric acid. Notice that only the first step is strong, or it's 100% ionization for the first step. But the second step, it goes both ways. Did you notice that? Okay. So for sulfuric acid, it is classified as a strong acid, but only the first step is strong. The second step is not. Second step is actually weak. Okay. Let's summarize this Brønsted-Lowry definition using the model you see over here. So basically, this HCl will lose the proton. This proton will be lost, and the H2O, water, will pick up the proton. When HCl loses the proton, it becomes chloride. H2O picks up the proton, it becomes hydronium ion. Okay. For any acid, as I just reviewed, at any generic acid, when you react with water, okay, it becomes A- and the hydronium ion. When you write the equilibrium constants, okay, please do not include water, because water has a constant concentration. It will not change. Rather, we write the equilibrium constant for acid. This subscript A means it's equilibrium constant for acid without water. So you write this equilibrium constant without water. Okay. For strong acids, theoretically speaking, the Ka should be indefinitely large. However, in reality, though, you do have a large, very, very large number, much, much greater than 1. For weak acids, Ka is smaller than 1. Usually, it's much smaller than 1. For weak acids dissolved in water, it follows exact the same pattern, reacting with water and generate hydronium ion for each one. And for the acid, it loses the proton. The acid loses its proton. Okay. The only difference between strong and weak is, do you ionize 100%? Weak acids do not ionize 100%. So that's why you use this equilibrium. Use the equilibrium sign over here. Okay. If you want to look at the equilibrium constant, usually it's really, really small, as you have observed over here. Right. We just discussed some strong acids, some weak acids. What about strong bases? Strong bases follow the same definition. It ionizes 100%. So what is strong base? Strong, it's an absolute concept. That means 100% ionization. That's it. Okay. We have many strong bases, but most of those bases they actually come from group 1A and group 2A metal oxides. As you see, we have listed 6 of them over here. If you look at your periodic table, actually we have a lot more. All right, so look at here, this comes from 2A, group 2A, and this comes group 1A. Actually for group 1A, we should add 2 more, okay? So rubidium hydroxide, cesium hydroxide, these are also from 1A, and they are also strong bases. So basically you have 8 of them to memorize. Okay. What about weak bases? Weak bases is usually, the examples for weak bases, they are based on ammonia or the derivative of ammonia. For example, when ammonia reacts with water, for bases, remember, all bases, okay, when you react with water, you are going to pick up, the basis itself is going to pick up hydrogen ion. So here, because initially you are neutral, so now you become positive charge, becomes this NH4 plus. And the water, in this case, will donate that proton. So it has 1 less H plus. Okay, so the charge becomes negative. That's hydroxide over here. It always follow the same pattern. All right. So for ammonia, you see that's NH3. What do I mean derivative? I just mentioned the weak bases, they are usually the derivative of NH3. What do you mean? Because NH3, if you write the Lewis structure, it looks like this. Okay, you can also write the long pairs over here. Okay, but you don't have to. So you have 3 hydrogens attached to that nitrogen. So up to 3 of those hydrogens can be replaced with hydrocarbon, okay, which means hydrogen and a carbon combination. So you look at this, the second aniline, NH2, that's 2 hydrogens still over there. One of the hydrogen is replaced with the hydrocarbon C6H5. That's a benzene ring, by the way. Okay. So for the next step, next example, dimethylamine. So 1 hydrogen is retained. The other 2 hydrogens are replaced with 2 methyl groups, 2CH3. Okay. So that's how you can recognize this as the derivative of NH3. Similarly, you look at the methylamine. 1 group is replaced with CH3 and the 2 hydrogens replaced. All right. So when you look at the next guy, pyridine, this is kind of special, okay? For pyridine, if you really want to know the structure, it's actually looks like this. So it's kind of different. All right. But basically, it's the nitrogen-based weak bases. All right. You also noticed one thing, as we emphasized, for acids and bases, according to Brønsted-Lowry definition, you always react with water. After you react with water, acid will lose the proton and it become a species that has 1 less proton. And these 2 species are called a conjugate acid-base pair. So this guy is called a conjugate acid. That one is called a conjugate base. Okay. Now another pair, I'm gonna box this up. H2O and H3O plus. They are also called conjugate acid-base pair. But in this case, this is the conjugate acid, and H2O is the conjugate base. You notice the difference between a conjugate acid-base pair is 1 proton difference. The conjugate acid has 1 more proton. The conjugate base has 1 less. Look at this model over here, which shows you the same thing. Conjugate acid, conjugate base. Okay. For water, you do remember they are also conjugated. That's conjugate base, this conjugate base, and the other guy is the conjugate acid. So these 2 is 1 pair, the other 2 is 1 pair. All right. For the base, one more time. We've been doing this for a long time already, right? Base serve as proton acceptor. So after you accept the proton, you become conjugate acid. So this is conjugate acid base pair. Then for water, it's also conjugate acid base pair with the hydroxide. Okay, you might have noticed at the top, water serves as the conjugate base, and the bottom, actually here, it serves as the conjugate acid. So water, which can serve as both a conjugate acid and the conjugate base, we call this amphoteric. So amphoteric, this property is called amphoteric. So water is amphoteric, which means it can serve as an acid, conjugate acid, or a conjugate base under different situations. To understand the relative strength of acids and bases, we need to understand the relationship between an acid and its conjugate base. All right. If we revisit the ionization of HCl, we know that HCl is a strong acid, and the forward ionization goes to 100%. Another way of looking at this is that chloride ion that is generated as a result of HCl ionization by reacting with water, they have zero chance to go back. So let's look at this situation. For example, you have HCl, all right, you react with water, okay, so then you're gonna go to right side 100%. So basically what this tells you is this is 100% going to the right side, okay. So chloride has no chance to pick up one proton from the solution to become HCl, okay. So in other words, in this conjugate acid base pair for HCl and the Cl minus, the conjugate acid and the conjugate base, this is conjugate base over here, okay, that's the conjugate base over here. All right, the conjugate acid is strong. Remember, strong means 100% ionization, or strong acids are the strongest type of acid. But when you look at the corresponding conjugate base, okay, of that strong acid, chloride has no ability to pick up a proton, which means this base, this conjugate base, chloride, is really weak. It's so weak as no chance to pick up one proton and become HCl. So in other words, the stronger the acid is, the weaker the conjugate base. The opposite is also true. The weaker the acid, the stronger the conjugate base. For example, the strongest type of acid, which is so-called a strong acid that ionize 100%, they will have the weakest bases. Okay, so these are strong acids. Okay, so the conjugate base will be really, really weak. All right. Similarly, for the really weak acid, the conjugate base will be really, really strong. Okay. Another concept I would like to introduce to you is hydronium ion is the strongest proton donor in water. So any acid that is stronger than hydronium ion, they will react with water and become hydronium ion. They cannot exist in any other form. So some acids might be stronger than the other one, but they will show the same acidity. For example, we do know perchloric acid is stronger acid. This is stronger than HCl, and both of them, as we learned, both of them are strong. Okay, but in water, they are strong acids. Okay, this is strong acid. This is also strong acid. But in water, we cannot tell apart which one is stronger or not, because both of them will have to react with water and become hydronium ion to show the acidity. So this effect is so-called a leveling effect, which means for any acid that is stronger than hydronium ion, they will be leveled to the same of the same acidity of hydronium ion. Okay, and for the bases that is stronger than hydroxide, they will also show the same basicity as hydroxide. So that's so-called leveling effect. Let's quickly summarize Brønsted-Lowry definition of acids and bases. Brønsted-Lowry acid will react with water and produce hydronium ion. Brønsted base will react with water and produce hydroxide. And that's exactly how they show the acidity and basicity, respectively, in water. We also emphasized one property about water, which is in these two situations, water will serve as a Brønsted-Lowry base and a Brønsted-Lowry acid, respectively. Water can also serve as an acid and base in the same reaction as you see over here. When one water molecule is reacting with another molecule, it can ionize to hydronium ion and hydroxide. So one H2O is picking up one proton from the other H2O, and this reaction is so-called autoionization of water. The equilibrium constant for this reaction is extremely small. At 25 degrees C, okay, it's 10 raised to negative 14th, which is really, really small. Okay, do remember the first portion of this equation is always valid because it's by definition the equilibrium constant is the product over the reactants, which you don't write because they are pure liquid. Okay, but the right side, this number is only correct at 25 degrees C. At different temperature, that number will change. In chapter 14, we emphasized the equilibrium constant will change with temperature. The pH scale is defined based on the negative log of the hydronium ion concentration, or you can simply write negative log of H plus concentration. Okay. The pOH, P, remember, is just a negative log. So pH is negative log of hydrogen ion or hydronium ion. pOH is negative log of hydroxide. Since Kw is hydronium ion concentration times the hydroxide concentration, and at 25 degrees C is 10 raised to negative 14, so you would know pH plus pOH is 14. Again, it's at 25 degrees C for this side. Okay, pKw is always the same as pH and the total of pH and pOH, because that's by definition. But only at 25 degrees C, pH plus pOH is 14. Let's do a simple calculation. If we know a solution has a pH of a certain number, in this case 11.70, can you calculate the hydronium ion concentration in the hydroxide? Okay, we do know what the pH is defined as, so we should be able to do the opposite, because we do know this is the definition of pH. So mathematically, you should know hydronium ion concentration is 10 raised to negative pH. Similarly, for pOH, the hydroxide concentration would be the 10 raised to negative pOH. Okay, so that's what we use to do the definition for the hydronium ion concentration, and the unit is molar. Okay, similarly, you can do this in a different way. For example, you know pH plus pOH is 14, so pH is 14 minus pOH. That's another way to do it. Okay, so this will gives you 2.30. So this can So I mean the POH is 14 minus pH. Okay. All right. So you do know OH minus concentration will be 10 raised to negative 2.30. This will also give you 5.0 times 10 raised to negative 3 molar. So that's the another way to do the calculation of a hydroxide. Okay. So for this question, you notice the pH is greater than 11 greater than 7, so that means it's basic. Basic means the hydroxide concentration is greater than that of the hydronium concentration, as you can see from this calculation, and this is consistent with our calculation. One thing I want you to be 100% clear: in any water solution, you will always see both hydronium ion and hydroxide. They cannot be zero, because the product of these two will be 10 raised to negative 14. Any one of this, because the product of these two is 10 raised to negative 14, however small that is, any of this hydronium or hydroxide concentration can never be zero. They always coexist. We previously discussed a lot about the acid ionization according to Brønsted-Lowry definition. Okay, so if you want to write a generic equilibrium constant, because this is an acid, that's why I use Ka, it will be A minus times the hydronium ion concentration divided by HA concentration. Remember, do not include H2O, which is a pure liquid. Okay, so for this specific case, nitrous acid, which is weak, you can write an equilibrium constant this way. And this can be used for the pH calculation for a weak acid, which we will discuss later on. But now, let's talk about one example for the pH calculation for a strong acid. Because the first thing you got to realize, hey, that guy is a strong acid, okay? And for a weak acid, hypochlorous acid is a weak acid, because it's not one of the 6 that I asked you to memorize. So you would assume that's a weak acid. We do have some other strong acids. They are actually super acids, but you simply assume anything that you don't memorize as one of the 6 will be a weak acid. Okay, for example, hypochlorous acid. Calculation for the pH for the strong acid is very straightforward, because strong acid ionizes 100%. So for this reason, the hydronium ion will be exactly the same as the initial concentration of the strong acid. So when you do the calculation, it would be pH equals negative log of hydronium concentration, which is for strong acid, it's the same as the initial acid concentration, negative log 0.100. This gives you 1. Okay. For the weak acid, you will have to use the so-called rise table or ice table to figure out what the acidity is. All right. Here's how you build the ice table. For the ionization, you build the ice table. Here's the initial concentration. Before the ionization, you have almost no H+. You still have a little bit because of all the ionization of water, right? And almost you have 0 anion over here. So the reaction will shift to the right side to establish equilibrium. So everything is a 1:1 ratio. So you can do minus x, plus x, and plus x. Put everything together and do the Ka definition, because the K is really, really small. So when you do the calculation, you can use the small x approximation, okay? Which means x compared to the initial 0.1 is negligible. So when you do that, this will become x squared divided by 0.100. So then you can do the calculation. You can find out that x equals this number. Okay. Then you can do pH calculation. That's also relatively straightforward. Okay. So let's summarize this. For a strong acid, the pH, for example, in this case, in hypochloric acid, the pH is 1. For the same concentration, for hypochlorous acid, the pH is much bigger. It's 4.27, which is expected. Now, let me introduce to you another concept, which is called a percent ionization. So what is percent ionization? It is the quantity of the substance that is already ionized divided by the initial concentration, which means the concentration before ionization. So if you look back to the previous example, okay, so what is the percent ionization? The portion that is ionized is X, okay, because X becomes, you see, that's the ionized portion. So X is the portion that is ionized. Initial concentration is 0.1, right? So in this case, it would be 0.100. That's the initial concentration, and X is the ionized portion. And this times 100%. This gives you ionization percent. If you want to do the calculation, you do the calculation, you'll find out the ionization percentage for this weak acid, HClO, hypochloric acid, is really small. Okay, so that's how you can do the quantitative calculation. But by definition, though, qualitatively, the percent of ionization will decrease as the acid concentration increase. As you can see over here, when the acid concentration increases from left to right, the percent of ionization actually decreases, as you can see over here qualitatively. Let's look at another example about percent ionization. So calculate the percent ionization for a weak acid. You got to recognize this as the weak acid, okay? Different concentration you see over here. Okay, so we can do two calculations. Use the Rice table, exact the same way. Okay, so how do you use the Rice table? The Rice table means you can use generic ones. You can do HA. All right, you can also do this. Okay. And if you look at different textbooks, they might write direct ionization, which is also okay, right? Because water will not be included in the calculation anyway, because it's in liquid phase. The other is aqueous phase, aqueous phase, aqueous phase. So aqueous over here, then you have NO2 minus and hydronium ion here. When you do the ice table, so this is initial concentration. Let's do initial concentration for 1.28. All right, so this is 0. This is almost a 0 here. Then you build the ice table. This is minus X. Here would be a plus X. Then this would be plus X as well, right? For the last row would be 1.28 minus X. Here, this would be X, then X. So when you do the Ka expression, Ka will become X squared divided by 1.28 minus X. And you'll notice the Ka is very small, as you can see over here. So we can use small x approximation. That means 1.28 minus X is almost the same as 1.28. So you cross this out. So you can do the calculation again the same way. X will be the square root of 1.28 times Ka. So you can do the calculation this way. Then the ionization percentage is X divided by initial concentration 1.28 times 100%. So that's how you can do the calculation. Okay, I know this PowerPoint does not show you the details, so that's why here I'm showing you the details. For the lower concentration, we use 0.0150 in place of that 1.28. You can also do similar calculation. Okay, as I said, the ice table for the right side will be exactly the same, because for this ice table, I'm going to write this just briefly, okay? But you do realize one thing though, water is pure liquid. You don't include it, so we cross it out. You build the same ice table, initial concentration, then this is about 0 for the hydronium ion. Why did I say about 0? Because you do see a small concentration coming from the water autoionization. So that's why it's not absolutely 0. It's almost 0. Okay, but this guy is 0 for nitrite. So minus x. Then you have a plus x plus x. So we end up with exactly the same thing, no matter how you write the ionization equation. Okay, so on the left side and on the right side, you end up with the same Ka expression because H2O is not included. So you can actually do the calculation of percent ionization, and the result is 1.77% for higher concentration. And for lower concentration, much lower concentration, you have a much higher percent ionization. So basically this calculation shows you one thing we already showed you in this diagram, that tells you when the concentration of the acids increase, okay, the percent ionization actually decreases. When the acid becomes more diluted, the percent ionization actually increases. Now let's switch to the equilibria for weak bases. Okay, the concept is slightly different, but the calculation is almost exact the same. As you can see, first you do remember it's a base. So for base, you're going to generate hydroxide. If for any base you generate the hydronium ion, that means you have written the wrong equation, which is really, really important. Okay, all right. So when you build the ice table, you will use the Kb expression, because this whole thing is the base ionization. This is base ionization. Okay, so that's why you are going to use Kb. For any base, it must be Kb. For any acid, ionization must be Ka. Okay, do you remember? You also notice the water is not included because it's a pure liquid. Okay, let's do the calculation for one example. All right, so as for strong base, it's very easy. For strong base, the strong base, I'm going to write this lithium hydroxide. Okay, once you dissolve in water, it goes 100% to the right side. So because it's 1:1:1 ratio, after the ionization, there is no more lithium hydroxide inside. They have become 100% lithium ion and hydroxide ion because it's a 1:1 ratio. So hydroxide for this strong base will be the same as this initial lithium hydroxide concentration, or in another word, it would be 0.200. So your POH, not pH because we have hydroxide rather than hydronium ion concentration, it would be negative log 0.200. Okay, then what is pH? pH will be at 25 degrees C, 14 minus POH. That's how you do the calculation for a strong base, which is quite straightforward. For the strong base, very straightforward. For the weak base, you will have to do the Rice table. Okay, all right, so let's set up that Rice table or ice table. For the base, over here, you have no option. You have to react with water. All right, you have to react with water. For the acid, you can do direct ionization as I showed you, or you show the equation of reacting with water. But over here for the base, the weak base, you'll have to show it reacting with water, which generates the ammonium ion and hydroxide. So we build ice table or ice table exactly the same way. That's your initial concentration, and here is a 0. Okay, so that dashed line, that means 0. Hydroxide, it's almost 0. Why? Because you have very small amount coming from the water autoionization. Everything is 1:1 ratio. To remember, you do not write anything in this column because water is a pure liquid, right? So that's why you have negative x here, plus x. You put everything together, it's very similar to what we did to the acid, to the weak acid equilibrium. The difference, Kb, not Ka. So you write the same thing, x squared. Do you remember? Because Kb over here is very small, so we can use small x approximation. In other words, this x compared to initial 0.2, it's negligible. In other words, you can rewrite this thing as this. So that's how you can do the calculation of x. Okay, so x, to remember, what is x? Hey, x corresponds to what? To hydroxide concentration in the base ionization. In acid, x is the hydronium concentration. So that's the biggest difference. So you find out the x, then you can calculate the, of course, the percent ionization. You can also do the pOH calculation, right? So pOH, remember here for base ionization, x is the hydroxide concentration. So it's negative log x over here. That would be a negative log 0.0019. Okay, this is 2.72. This is pOH. If I asked you to calculate the pH, pH would be 14 minus 2.72. This gives you 11.28. Okay. This question asks us to do the calculation for the percent ionization, and we can also do that. It turns out to be a very small number. For the pH of very dilute solutions, we have to consider the hydronium ion coming from the water autoionization, because in this case, that is significant. For the previous cases, all the previous cases we discussed, the water autoionization contribution have been neglected. Let's quickly go over this example of the dilute acid, the extremely dilute acid. Okay. For the dilute acid, remember, the HCl has already ionized, and this will produce exactly the same concentration of hydronium ion. That means this 1.0 times 10 raised to negative 8 molar of hydronium ion is already produced. There is no equilibrium to establish because HCl is strong. It ionizes 100%. Okay. Now for the water ionization, you will have to consider the equilibrium. How much is generated? So we assume it's X of hydronium ion is generated. Remember, hydronium ion and hydroxide is 1:1 ratio. That's why you will have X, which is exactly the same amount of hydronium generated from the autoionization. Okay, so you write the Kw representation using the H plus, which comes from two sources, one from the strong acid, which is the 1.0 times 10 raised to 8. Okay, then the other one comes from the autoionization, which we assume to be X. So you do this equation. Then you solve for quadratic equation, and you find out hydronium concentration is 1.05 times 10 raised to negative 7. Okay, do remember, this hydronium concentration is the total of the contribution from both the HCl and the water autoionization. That's how you get that. Okay, you calculate X, then x plus 1.0 times 10 raised to negative 8. You get 1.05 times 10 raised to negative 7. Then you calculate the pH. It gives you 6.98, which is very close to neutral pH 7 because the acid is very diluted. For polyprotic acid, we realize the acid will ionize stepwise. For example, for sulfuric acid, step 1, it ionizes and deprotonate 1H+. The first step, as we learned, is a strong acid. A strong acid usually, according to the theory, it goes to the right side 100%. You should not expect to have a Ka, but in reality though, it just tells you the Ka for that step is really, really large, as we briefly explained already. Okay, so a lot of times they simply do not include a Ka, but in reality, you do have a Ka for that step. Okay, a lot of times they simply give you Ka2 or simply Ka. If they write Ka, you still need to realize that is the K for the second step. Okay. Sulfuric acid has 2 protons to deprotonate, so we call this biprotic acid. We also have examples of triprotic acid like a phosphoric acid. Okay, as you can take note of, the Kas will decrease from Ka1 to Ka2 to Ka3. Okay, so you see Ka1 is 10 raised to negative 3, Ka2 10 raised to negative 8, Ka2 10 raised to negative 8, Ka3 10 raised to negative 13. So Ka1 is much greater than Ka2. Ka2 is much greater than Ka3. We have some other examples which gives you a much smaller difference between Kas. Okay, as you see in the next case over here. When you calculate the pH for a polyprotic acid like a biprotic or triprotic acid, if the Kas are very different, or in another word, in this specific case for carbonic acid, Ka1 is much greater than Ka2, then the ionization from the first step is gonna be much greater from the second step. So when we do the calculation of the pH, the ice table will be based on the first step ionization only. For carbonic acid, the first step ionization by reacting with water, it gives you hydrogen carbonate ion and hydronium ion. That's the first step. And the K for this step is Ka1. That's Ka1. Okay. Do remember, water is pure liquid. You should not include anything in this column. That's how you build ice table. After you build ice table, because Ka is very small, so you do the small x approximation, which means this x can be crossed out. You can calculate the x. Do remember, in acid, the x corresponds to the hydronium ion concentration. So the pH is simply the negative log x. For base, it would be pOH equals negative log x. All right. So that's how we do the calculation for a polyprotic acid that has very large Ka1 compared to Ka2. So far, we have discussed in great detail about how to calculate the pH for a strong acid or a weak acid, a strong base or a weak base. Now let's discuss qualitatively the factors that will affect the acid strength. When you compare the sulfurous acid H2SO3, which is a weak acid, with the sulfuric acid, which is a strong acid. Again, strong acid does not mean Ka is infinitely large. It just means it's really large. Okay. Why is that? So we can actually analyze the structure and know why. Okay. So when you look at the electronegativity of this oxygen, all right, and the atom that's attached to it. You have a chlorine over here. But if you have two oxygen, you have one extra oxygen that's pulling electrons away following this flow. Okay, so the hydrogen ion is more easily ionized because electron density is being pulled away by more oxygen in the successive mode. Right? If you have two extra hydrogens compared to the oxygens compared to the first one, then more electron density will be pulled away from this hydrogen ion, which means the acid becomes more easily ionized. Remember, electron density is pulled away. That means hydrogen is almost becoming H+, which is the ionization process. All right. So that explains to you why for an acid like this, HXON, if X is the same, the larger or the more oxygen you have, right, the larger N will give you stronger acid. Okay, because you will have more oxygen pulling electron density away from that hydrogen in successive mode. Now let's look at a different situation. What if you have the same number of oxygen but different number, different X over here? So let's look at that. For example, you have HClO, HBrO, HIO. Which one will give you the stronger acid? We analyze this using the same electronegativity. You notice that this guy is chlorine and this guy is bromine, okay, and this guy is iodine. Okay, the electronegativity of chlorine is greater than that of bromine, and that of bromine is greater than the electronegativity of iodine. So with the same number of oxygen over here, in this case is one oxygen, you can have more than one. Okay, then the difference actually reside in the heteroatom, chlorine, bromine, and iodine, because the electronegativity decrease from top to bottom for chlorine, from chlorine to bromine to iodine. That's why the ability to pull away electron density from hydrogen in a successive motion will decrease from top to bottom as well. So the acid strength will decrease from top to bottom, as you can see from comparing the Ka as well. Okay, so what if you have, for example, what if you have two oxygen? Would the acidity stay in the same trend? Yes, it will be exactly the same. So now you're gonna, if you have a two oxygen, that means this is connected to another oxygen, this is connected to another oxygen, this is connected to another oxygen. However, it does not change the difference. The difference is you will look at the difference, which is the X over here. The larger the electronegativity for that X, then you will have stronger acid. So the HClO2 will have a stronger acidity than HBrO2. It will also be greater than HiO2. Can you change 2 to 3? Yes, because the difference will reside in the X only. So if you change to 3, the acidity will stay in the same trend. If you change to 4, it will be exact the same trend. Okay. Now let's look at one more example. Look at the. Now let's look at one more example. Okay. In this example, for example, you have. What about the binary acid? For example, HF, HCl, HBr, and HI. Can you arrange them in the increasing acidity, okay, in strength? So how do you do that? So you might expect, because F electronegativity, That's what we used in the previous arguments, right? Electronegativity is actually, when you look at the trend, its fluorine is greater than that of chlorine, greater than bromine, greater than iodine. But when you look at the acidity, it's not HF is stronger than HCl, HBr. The acidity actually is the opposite trend. So that's the strongest in the series. And the HF is the weakest in the series. So what happened? Because actually you have two factors competing against each other. The first one is the electronegativity. The second one is the stability of the ion that is generated. For example, for HX, X being fluorine, chlorine, bromine, and iodine, right? When you react with water, okay? So what's going to happen is it will become hydronium ion and X minus, okay? So what happened for iodine is, if this is iodine, iodine is much, much bigger than Br minus, then Cl minus, then F minus. See, the size from top to bottom over here, the size of the anion, it actually decreases. So this anion size decrease, okay, size decreases from top to bottom. So the stability of the anion actually decrease as well. So that tells you I minus is the most stable, and here F minus is the least stable. So for this reason, although in terms of electronegativity, HF is favored, but in terms of the stability of the ion that is generated, I minus is favored. And it turns out the stability of the anion, or the product, right, of the I minus override the electronegativity. So that's why you see some kind of unexpected the trend of acidity for HX series. Next, we are going to look into the properties, acid-base properties of salts. Okay, when you have a weak acid, okay, you react with water, you generate a base and hydronium ion. And we also analyzed one thing about a conjugate acid and base. The stronger the acid, the weaker the base. Actually, the strongest acid, which is so-called strong acid because they ionize 100%. Strong acids are the strongest type of acid. For example, HCl, when you react with water, okay, you will go to the right side, 100%. And in other words, as we analyzed before, Cl minus has no chance to pick up a proton. Okay, so Cl minus will be neutral because you cannot react with the H plus or hydronium ion. You have no ability to affect the pH. So Cl minus is neutral. However, in the case of HF, you look at the arrow because you have an equilibrium that is established. So when you go to the right side, the F minus does have the ability to pick up one proton and go back. So F minus have a little bit stronger basicity than Cl minus because the conjugate acid is HF is weaker than HCl. We analyzed that already. So now, when you analyze NaF, okay, NaF when it dissolves in water, you generate Na plus and fluoride. Na plus portion is neutral. So this will not affect the pH. Na plus will not affect the pH. But as we analyzed above, F minus is basic. Okay, remember the difference between basic and the base. Do remember Cl minus. Yeah, that is a base. And F minus, it is also a base. But Cl minus is not basic because this base is so weak. It comes from a strong acid. So this species is neutral. It's not a basic. You see the difference? But F minus, it's base. It's also basic in this case. Okay? All right. So when you dissolve NaF in water, it serves as a base with Na plus being neutral. So when you write the equation for this, you actually write F minus only. Do not include the neutral portion. It reacts with water and it generates HF and the hydroxide. Remember, hydroxide is why a solution will display basicity. Hydronium is why a solution will display acidity in water. Let's look at a few more examples. All right. Remember NaCl, when you dissolve in water, it becomes Na plus, which is neutral. Cl minus, as we analyzed before, it's also neutral. So NaCl is neutral, that's why. All right. What about Na4 plus and the chloride minus? Chloride, that's the Cl minus. Okay. So when you write this, Cl minus is neutral. Okay. NH4 plus is acidic. Why? Because when you write this equation over here, NH4 plus, it reacts with water. All right. Then you will generate NH3 and hydroxide. You see that? This has an equilibrium because NH3 is a weak base. Okay. So the acid conjugate acid, which is ammonium ion, that's the conjugate acid, will actually show acidity. This is a weak base. The conjugate acid will show acidity because the weaker the acid, the stronger the base. The weaker the base, the stronger the conjugate acid. That's how conjugate acid-base pair works, and we talked about that already. Okay, so we already analyzed the NaF, and for the other examples, I want you to read on your own because it's weak and versus weak. It will depend on the Ka compared with Kb. Okay, we're gonna skip that one because it's more complicated than you need to know. Okay. So far, we have learned the salts can also act as an acid or a base. Can we do calculations of their corresponding pH as well? Yes, we can. But we have to be able to calculate the corresponding Ka and the Kb according to what you will see over here. Okay, basically what this tells you is for the base, oh, that's a conjugate base, remember, okay? This is conjugate base. But in this conjugate base, no Kb will be given for you. You see, usually what's going to be provided is the Ka for the original acid. A minus is the conjugate base, but they don't give you the Kb. Usually they give you the Ka. So you will have to calculate the Kb according to this equation, which tells you Kw is Ka times Kb. So if you need to calculate the Kb would be Kw over Ka. You see that? Vice versa, okay? If they give you the conjugate, so if this is known, that's how you do the calculation. You can also do the Ka calculation according to Kw divided by Kb. If, for example, so I give you NH4 plus, okay? So what is the Ka for this? Oh, Ka usually is not provided for this ammonium. Rather, the Kb for NH3 will be provided. So if you want to calculate the Ka for ammonium ion, you will do this equation. Okay, similar to what we talked about for the other case. Let's look at one example. So in this case, we want you to calculate the pH for sodium acetate. The first thing you got to realize, what is sodium acetate? So sodium acetate, of course, you don't have to write the whole thing, but if you do, it's fine. Okay, so that's the formula as you see over here. But the important thing is this portion comes from acetic acid. So that's why the anion is called acetate. Okay, acetic acid is a weak acid because it's not one of the 6 strong acids that ask you to memorize. So weak acid would have a conjugate base that will display basicity. So remember, when this thing dissolves in water, okay, it will become this. But do remember, this is not what you're going to use to do the calculation. This just shows you why this thing will be basic, because Na plus is neutral. Okay, this guy is basic because the conjugate acid is weak. Remember, the weaker the acid, the stronger the base. So that's why acetate demonstrate basicity. And when you do the calculation, you can actually simplify this. You can write, hey, NaA, this A means acetate, and for this portion, Na plus, you're not going to consider that in the rise table. Rather, you're going to use A minus, okay, for the pH calculation. Do remember, this whole thing serves as a base. So when you build the ice table, that's what you do. You can replace this with A minus, okay, if you want to, and this will become HA. But if you want to write the whole thing, it's also okay. So you build ice table, as you see over here. You do not include H2O, which is in liquid phase. Everything else is aqueous solution. Okay, so you build ice table exactly the same way, and you do know you need to use Kb because this whole thing is serving as a base. That's why you use Kb, not Ka, although Ka for acetic acid is provided. But you're not going to use that one because you're going to use Kb for base ionization. So do Kw over Ka, you get your Kb, and you do the calculation using the small x approximation. That's exactly how you do it. Do remember, this is base. So after you do the calculation of x, that corresponds to OH minus concentration. So you do POH first, then do pH is 40 minus POH. So you have the pH calculated, which is 9.25 greater than 7, which makes sense for sodium acetate because we analyze this to serve as a base, right? So you expect the pH to be greater than 7 at 25 degrees C. So that's it for today's discussion. For more examples of the pH calculation, you can look at the problem sets, and the answer key is also attached. And have a good day. Bye.